So on this lecture video, we will try to solve. We will then continue with our lecture with fixed end forces of a member. So just like what we did with beams before, before we move on with analyzing solving the displacement of each span of a beam, we need to solve the fixed end forces of each member span. No, ganon din sa ating frame. So solve natin yung fixed end forces on its local coordinate system, and after doing so, we'll have to convert it on its global coordinate system. So halimbawa, ito yung ating member, inclined member, para madali na nating ma-apply. Parehas din, apply. This method is both applicable on both inclined and horizontally inclined or flat members. No? So identify first your positive x and y axis or coordinate axis. Then, halimbawa, meron kang member loads dyan, identify your x and y components of the applied loads. Okay, nasan yung positive x, nasan yung positive y. Then, plot off your end forces and moments, or your fixed end moments on its local coordinate system. So, local coordinate system, ayan yung ating x, ayan yung ating x, ito yung y, then ito yung moment. Then, number it by normal, shear, and moment. So, we have QF1, QF3, QF2, near node, then far node, QF4, QF5, and QF6. As an example, we have here a member BE. Member BE, name it as member M, having a uniformly distributed load of 1.5 kips per feet vertically downward, or directed vertically downward. No? Example of fixed end moment in an inclined members. No? Pag horizontal members naman yan, tapos merong applied axial force dun sa gilid, consider nyo yon na part ng ating analysis. No? But with this, ito lang naman yan. Fixed end moment in inclined members. So, halimbawa, member BE, member M. It has here vertical component of 16 feet, horizontal component, horizontal length of 30 feet, total length of 34 feet. Applied vertical uniformly distributed load of 1.5 kips per foot. Plot na natin yung ating fixed end moments. Your axial, FAB, FSB, A axial, S shear, M is moment. FSB, FMB. Then, FAE, FSE, and FME. Okay? Una lagi si axial, susunod si moment, susunod si shear, then last si moment. Now, if the member is not inclined, therefore, the end moments or forces on its local coordinate system is equal to the global coordinate system, is equal to its end forces and moments on its global coordinate system. Halimbawa, horizontally, yung ating member, meaning the end forces and end moments on its local coordinate system is equal to its global coordinate system. But if it is inclined, we still need to convert it by multiplying the local coordinate system fixed end forces to the transformation matrix, transpose transformation matrix. But later na lang yun. So with this member, meron tayong horizontal 30 feet, vertical 16 feet, identify the length 34 feet, Pythagorean. Yeah. Then cosine theta 15 over 17.88235, sine theta 8 over 17. Na-reduce ko na yan. Converting our uniform load on its x and y component. Vertical uniform load of 1.5 kips per foot. That is 1.5 times 34 is 51 kip, WR, resultant. Convert it on its x and y component. WR sine theta, WX is 24 kips. WY is equal to WR cosine theta, which is 45 kips. Perform our fixed end moment analysis, solving FAB or the actual force on point B and point E. Dahil uniformly distributed naman siya, wala naman tayong ibang loads within the member, then our axis is positive upward and positive to that side, positive x, then positive y upward and positive x upward over there. So, parehas na yung ating FAB at FAE. So, uniformly distributed naman siya. So, divided by 2 yung ating WX, that is 12 kips. The shear is FSB equal to FSE. So, WY over 2, that is 22.5 kips. Then, the moment. The moment is based on the Y component, no? Moment naman yan. Y component. WY times the length of the member divided by 12. Parang simpleng beam lang, no, on a fixed ends, fixed end supports, no. So that is WY times L over 12 giving us 1530 kips inch. So parehas yung point B at point E na moments dahil uniform naman siya. So okay lang yan. Yeah. WY over 12, 1530 kips per inch. Now, the fixed end forces or the fixed end moments is starting from the near node to far node. Again, follow your near far node condition on your member from node B to node E. So FAB, SB, MB, AE, SE, and ME. Then summate. Kung marami yung members mo, let's just say 5. Hanapin mo ulit lahat yon. Hanapin mo lahat ng fixed end moments ng bawat members. And we'll be needing them later on sa ating structure matrix. If the member is subjected to member loads. If not, there will no longer be a need for you to solve the fixed end moments and fixed end forces. I repeat, if your member is subjected to member loads, you'll have to solve for the fixed end forces or fixed end moments, just like here, just like what we did here. No, but if your members or your frame is not subjected to member loads, repeat, member loads, not joint load ha, member loads, we still have to solve with the fixed end forces and moments. So ito yung ating fixed end moment or fixed end forces of a member on its local coordinate system. Again, this is only on its local coordinate system. Okay? After computing the fixed end moments and fixed end forces of a member on its local coordinate system, next is for us to convert that fixed end forces on its global coordinate system. Remember, QF is only on its local coordinate. Convert natin siya into global. How do we do that? Converting the fixed end moments and reactions of a member from local coordinate system to global coordinate system is simply multiplying it to the transpose transformation matrix of such member. So this time, we will now be solving for the fixed end reaction. The fixed end reactions or the fixed end moments on its global coordinate system, after solving FEM, converting QF local to FF global, FF global coordinate system is simply equal to the transpose transformation matrix of that member times the solve a fixed end moment on its local coordinate system. So yun na yun. Then summate to solve for our fixed joint force matrix. So, parang ginawa natin sa truss at saka sa beams. So after solving FF on each member, summation lang ang gagawin natin dyan to solve for PF, which we'll be needing later on to add it up on our structure matrix. So PF is basically the summation of FF, not QF. PF is the summation of fixed end reaction on global coordinate system. Okay? Meron na tayong PF. Now, we will then have to identify whether each joint of our frames is subjected to a joint load. Kung yung ating frame sa bawat joint ay merong identified joint loads. So, identify or all the known joint loads. denoting that as P sub k, or known forces. These are your known forces. So remember, from our analytical model, we start our number with joints which has known joint loads. So starting node 1, ay node 2 to node 3, those are your known joint loads. So tignan natin kung meron talagang applied loads doon on the joints, both axial, shear, and moment. After identifying your joint loads, or PK, known applied forces along the joints or the nodes, we could then start solving or completing our partition matrix or our structure matrix. Solving the unknown joint displacements, which are your rows which carry the rows of our structure matrix that carries the known joint loads, no? That is basically your structure matrix is the forces equal now to the structure matrix times the displacement plus PF. Take note of this, PF, if there was an applied load along a member. Kung yung entire frame mo ay walang member load, tanggalin natin yung PF. Okay? Remember, kung yung entire frame does not carry, or the problem does not have any member loads, tanggalin natin yung PF. Pero kung meron, lagay natin yung PF. So for our partition matrix, the above row are your known forces. The below is your unknown forces. Then S11, S12, 21, 22, unknown displacement, known displacement. Unknown displacement, known displacement, PF, corresponding to the number of rows which has the unknown displacement and known displacement, then PF below. Okay? Then PF below. Okay? Again, dk, lahat nung mayroong sub na k are known displacement along the joints or nodes. Then pk are known forces along the joints or nodes. So halimbawa, meron tayong induce or introduce settlement or deflection along a support or along a member, nandito yan sa dk. Pag wala, lahat yun, of course, are zeros. Understandable naman na that those are zeros kung yan ay fixed. Okay? So solving for the unknown displacement, basically the known forces equal now to the structure matrix S11 based on our partition times the unknown displacement plus the S12 times the known displacement plus the fixed end forces PF, no? Summate muna natin itong dalawa bago natin i-transpose to subtract with PK. Then divide that with S11, or multiply that with the inverse of S11. Okay? Baka makalimutan ninyo dito muna bago ninyo i-transpose. Baka pagkabaliktad ninyo. So, S12 times dk plus PF kung merong PF. Kung wala, tanggalin na yung PF, then transpose. So, S12 times dk plus PF, summate, then transpose. Subtract pk with the summation of this. Then, multiply the inverse of S11 with the difference of these two to solve for the unknown displacement. So basically, the unknown displacement or the unknown joint displacement is simply equal now to the inverse of S11 times the difference of PK minus S12 times DK plus PF kung merong PF. Kung wala, tanggalin na lang. Kung walang member loads. Okay? Unknown joint displacement. Now, after solving the joint displacement, we will now be able to solve for the end forces, member end forces and member end forces and end displacement of each member or the actual member end displacement and end forces on both on its both local coordinate system and global coordinate system. Solve na natin yung displacement, hanapin na lang natin yung ating formulas dito. So solving for the end forces on its local coordinate system, Q, or the end forces on local coordinate system, is equal the local stiffness matrix of the member times the end displacement of a member on its local coordinate system plus the fixed end forces on its local coordinate system, yung FEM natin kanina, yung ating QF. How do we solve for the end displacement on local coordinate system? The end displacement on local coordinate system is basically, again, is the transformation matrix of the member times the end displacement of the member on its global coordinate system. Parang yung truss, ganun pa rin. End displacement on global coordinate is equal to the product of transformation matrix of a member times the end displacement of a member on its global coordinate system. Lagay na natin dito yung na-solve nating displacement kanina from our partition matrix. No? Okay? So, meron na tayong end forces at end displacement on local coordinate system. So how do we solve the end forces on global coordinate system? Solving the end forces on global coordinate system, that is F equal to the transpose of the transformation matrix, again that is transpose of the transformation matrix, times the solve end forces of a member from the local coordinate system. So, nung na-solve na natin yung end forces on its local coordinate system, we'll just have to multiply the transpose transformation matrix to solve the end forces on its global coordinate system. So, dalawang isosolve natin yan. Para later on, yung summation na lang ng F will eventually gives us the reactions at the support. Okay? Yun ang kailangan natin to solve the reaction yung F. Summation ng F, not summation of Q. Summation of F gives us the end forces on the support or the reactions at the support. Okay? So with that, after solving the end forces and end displacement at both local and global coordinate system of a member, we can then proceed now in solving the reactions at the support, which is denoted by our variable PU. Okay? The unknown forces or the reactions at the supports, that is your PU, equal now to S21 times the solved displacement or the unknown displacement plus S22 times the known displacement plus the end forces or the fixed end forces. Fixed end moments or the fixed end forces na compute natin. Kung merong member loads. Kung walang member loads, tanggalin ulit natin si PF. Ulitin ko, kung merong member loads, merong PF. Kung walang member loads, walang PF. Ganun lang naman yun. Okay? Kahit, halimbawa, the entire frame, walang member loads, or all of the members within the given frame, walang load, or walang member load, so walang PF. Pero, kung ang isa lang na member within the frame ang merong member loads, meron pa rin tayong, kahit iisa lang yon, meron pa rin tayong PF. Okay? Solving the reactions at the support is basically the structure matrix S21 times DU plus S22 times DK plus PF. Or, para mas mapadali, total na solve naman na natin yung forces on global coordinate system or member end forces and end displacement on global coordinate system, which is your F. solve na natin kanina, summate lang natin yon corresponding to the number of our unknown reactions at the supports. No? PU is equal to the summation of F, or N forces in global coordinate system. Okay? Okay. So with this particular material, I'll be sharing this one to you later on in our Google Classroom in a Google Drive link form. On this particular material, you'll be seeing here a manual or a procedure manual on how are you going to solve or perform matrix stiffness method on frames. Procedure for analysis. Using the concepts discussed in this particular lecture series, we can now develop the following step-by-step procedure for the analysis of the plane frames by the matrix stiffness method. Though the variables that you will be seeing here are not of the same that I'm using on our examples or on the previous lectures, but pretty much they have the same, uh, pretty much parehas na parehas yung procedure nila. Prepare an analytical model. So, ginawa na natin yon. Identifying its degrees of freedom, restraint ordinates, as discussed from our lecture 1. Recall that for horizontal members, the coordinate transformations can be avoided by selecting the left joint of the member as the beginning joint. Evaluate the structure stiffness matrix and fix joint forces on vectors for each member of the structure. So identify the local stiffness and identify the transformation matrix, the global stiffness matrix. Calculate the length of the directions and cosines and sines to compute for the transformation and the local and as well as the global. Then compute the member stiffness matrix on its global coordinate system. Global coordinate system. Dito, capital K yung ginamit for GK. Pero gamitin na lang natin yung binigay kong variable. More or less, they're just the same. The global stiffness matrix is basically the product of the transpose transformation matrix times the local stiffness matrix times the transformation matrix of such member. Okay? Then, if the member is subjected to external loads or member loads, then we'll have to compute the member fixed end force vectors or the fixed end moments. Computing the fixed end moments on its local coordinate system, then converting it on its global coordinate system. After which, summate it to compute for PF. Identify the member code numbers and store the pertinent elements K and FF, or the global and the N forces in their proper positions in structure matrix. Again, perform the analysis on year far nodes. No, then summate. Then the complete structure stiffness matrix. If the structure is subjected to joint load, then identify your joint load matrix, yung ating PK. Determine the joint displacements, just like what we did kanina. Compute the member and displacement and forces, yung kanina. Obtain member and displacement in the global coordinate system from the joint displacement using the member code numbers. Form the number transformation matrix. Form member local stiffness matrix. Determine the member and forces global coordinate system. If the member is attached to a support joint, then use the member code numbers to store the pertinent elements of the PF or the F. Check the calculations of the member and forces to support your reactions. How do we check that? Using the longer formula with the shortcut formula. Yung shortcut formula is the summation of F, or the fixed end forces, summation of member and forces on global coordinate system. Compare that with the calculation from your structure matrix on solving the support reactions. After doing so, that's it. You are now ready to solve. If you're familiar with the procedure, you will now be ready to solve frames using using matrix stiffness method. So by doing so, start or practice with this given problem. Practice problem. You're now asked to determine the joint displacements on joint displacements, member end forces, and support reactions for the two member frame shown below. So, halimbawa, meron tayong ganitong member. Basically, that is a statically indeterminate frame. So, gawin nyo lang, convert lang natin yung x and y component nito along the axis. And apply, ito yung ating known joint load. So, forth and so long. Hindi naman nag-vary yung length. So, okay na yan. Meron constant yung ating areas. Parehas yung member 1 at member 2. Ito yung ating analytical model. Lagi ko namang ibibigay yung analytical model para pare-parehas tayo ng analysis later on. So I will always give you the analytical models, quizzes and exams for us to have a balance or a incorporating analysis later on. So with this one, you may start practicing on this problem. So with this, I'll see you on our next lecture videos. This time we'll be discussing example problems involving matrix stiffness methods on frames. And bye-bye.